Hello and welcome to The Sleepy Scientist. I'm glad you found your way here tonight. Before we begin, I'd love to know, where in the world are you listening from? Let me know in the comments if you feel like sharing. If you're new to the channel, a gentle tap on the like button and a quiet subscribe would mean a lot. It helps more sleepy minds find their way here. And if you're already subscribed, thank you. Truly. Your support is what keeps these slow journeys going. Now, I do hope this video isn't so fascinating that it keeps you wide awake. But if it does, well, at least you'll have something interesting to think about while you wait for sleep to arrive. So tonight, as the world outside settles into stillness, we're going to explore a question that's as vast as the sky itself. Can we truly comprehend how big the universe is? We say things are big all the time. A big tree, a big city, a big mistake. The word rolls off the tongue easily, so does far, or even infinite. But most of the time, we're not really imagining anything close to the real thing, not when it comes to the universe. The truth is, our minds weren't built for this kind of scale. They evolved to notice how far away the next branch is, or how large an animal looks in the distance. Meters, maybe a few kilometers. That's the scale we're comfortable with. The familiar, the manageable. But out there in the vastness beyond our planet, distances stretch into millions, then billions, then numbers that don't just defy imagination, they quietly laugh at it. In this video, we're going to take a slow journey outward. From the ground beneath your feet to the edge of the known cosmos. We'll travel past planets and stars, glide through galaxies and cosmic webs, and drift gently into the regions where science becomes philosophy and space becomes a kind of poetry. This isn't a quest for hard answers. There may not be any. Instead, think of this as a guided float through immensity, a way to sit beside the biggest questions and simply feel their weightless beauty. Because sometimes the most human thing we can do isn't to understand the universe, it's to be amazed that we get to wonder about it at all. When you think about distance, what comes to mind? Maybe a walk across the street, a drive to the next town, or a flight across the ocean. We have a pretty good sense of these scales because they fit neatly into our everyday experience. A meter, a kilometer. These are things we can picture, things we've felt with our own 2 feet or seen roll by through the window of a car. But once you leave the Earth behind, those familiar measurements start to fall apart. The universe simply doesn't play by the same rules. It's not just big, it's astronomically big, literally. And trying to measure the cosmos with Earth-sized rulers is a bit like trying to measure the Pacific Ocean with a teaspoon. Let's start with something close to home, the distance from Earth to the Moon. It's about 384,000 kilometers. That number might seem large, but it's still within the bounds of human intuition. It's about the same as flying around the Earth nearly 10 times. Manageable, just. Now consider the distance from Earth to the Sun, about 150 million kilometers. That's so far that sunlight, travelling at the fastest speed anything can travel, takes over 8 minutes to reach us. It's such a foundational number in astronomy that scientists gave it its own name, 1 astronomical unit. It's a convenient shortcut for measuring distances within our solar system. Mercury orbits at about 0.4 astronomical units, Jupiter at around 5.2, and Neptune at nearly 30. These numbers help shrink the vastness into bite-sized chunks, at least temporarily. But the moment we leave the solar system, even astronomical units start to crumble. The nearest star beyond our Sun is Proxima Centauri, a small red dwarf just over 4 light-years away. In astronomical units, that's roughly 268,000. Not exactly a convenient number. You'd need a very, very large spreadsheet. Enter the light year. A light year isn't a measure of time, it's a measure of distance. It's how far light travels in a vacuum over the course of 1 year. And since light moves at around 300,000 kilometers per second, it racks up quite a total. In a single year, a beam of light will travel nearly 10 trillion kilometers. That's 1 light year. Just 1. When we say Proxima Centauri is over 4 light-years away, we mean that the light we see from it tonight left that star more than 4 years ago. If it exploded right now, don't worry, it won't. We wouldn't know about it until 4 years in the future. In this way, the light year isn't just a measuring stick, it's also a time machine. Every time we look into the night sky, we're not seeing the universe as it is, we're seeing it as it was. The farther away something is, the older the light that reaches us. We're not just watching space, we're watching history unfold in reverse. Now, for the truly curious, or mathematically brave, there's another unit you'll hear astronomers use, the parsec. 1 parsec is roughly 3.26 light years. It's based on a clever bit of trigonometry involving how nearby stars appear to shift against the background sky as Earth orbits the Sun. It's extremely useful for certain calculations, but if you're just trying to get a sense of scale, light years tend to feel a bit more intuitive, at least relatively speaking. Still, no matter what unit we use, kilometers, AU, light years, or parsecs, we quickly run into the same problem. The numbers get too big to truly grasp. You can say billions of kilometers, or millions of light years, all you want. But those figures don't land in the human brain with any real weight. They slip through the cracks of our understanding like water through open fingers. Our minds evolved in a world where the farthest horizon was maybe a few dozen kilometers away, where walking a couple of miles was a journey. It's no wonder that numbers like 100,000 light years, the width of our galaxy, or 13.8 billion light years, the age of the observable universe, feel more like abstract poetry than concrete reality. But this is why these cosmic rulers matter. They help us stretch the limits of our perception just a little bit further. They give us a framework for thinking about the unthinkable. They let us build a bridge, however flimsy, between our small human world and the vastness beyond. It's almost comforting, in a strange way, to know that even though we can't feel a light year or walk an astronomical unit, we can still talk about them, still think about them, still reach out with our minds and try however imperfectly to understand. And maybe in the end, that's what these units are really for. Not to bring the universe down to our size, but to help us stretch ourselves upward, just enough to brush against the stars. The universe has a speed limit, and it's not up for debate. No matter who you are, how much rocket fuel you burn, or how determined you might be, you're not going faster than light. Not ever. In the vast and silent courtroom of physics, the speed of light is the final ruling. Light travels at just under 300,000 kilometers per second. That's fast enough to circle the Earth 7 times in a single second. It's the fastest anything with energy or information can possibly go. Not only is it quick, it's fundamental. The laws of the universe are woven through this number. Even Einstein's most famous equation, E equals mc squared, rests on it. The c in that equation, that's the speed of light. It's more than a measurement. It's baked into the structure of reality itself. Now here's where things get strange in the best way. Because light moves so fast and so reliably, we use it to measure vast cosmic distances. But in doing that, something weird happens. Time and space start to blur together. In everyday life, distance and time are separate. You can walk 5 kilometers in an hour or drive it in 5 minutes. But in space, those lines get fuzzy. When we say something is 1 light year away, we mean it's so far that light itself takes a full year to get here. That distance is about 10 trillion kilometers, give or take. But since we're using time as a way to measure space, we're really talking about both at once. You can't say how far away something is without also saying how long ago its light began the journey. This is where the speed of light starts playing tricks on our sense of time. When you look up at the moon, you're seeing it as it was just over 1 second ago. That's how long its light took to reach your eyes. The sun is a bit farther, about 8 minutes away by light. So the sunlight that warmed your skin on a lazy afternoon actually left the sun when you were still brushing your teeth. But now zoom out further. The light from Sirius, the brightest star in the night sky, took about 8.5 years to get here. From the Andromeda Galaxy, over 2.5 million years. That's not a typo. You're seeing Andromeda not as it is now, but as it looked before modern humans ever walked the Earth. Every star you see, every glowing smudge in the sky, is an echo from the past. Space is not a backdrop. It's a time machine. Light brings us postcards from distant places, but they're never up to date. They're always late, sometimes unimaginably so. In this way, telescopes become time machines too. The deeper they peer into the universe, the older the light they collect. Astronomers have seen galaxies whose light has travelled for more than 13 billion years. These are glimpses of a universe that was still in its infancy, long before our sun or planet even existed. That's the mind-bending gift of the speed of light. It forces us to think in 4 dimensions, not just where something is, but when it is. Because light can't outrun time. It can only carry its memories forward, 1 second at a time. Now imagine this. If somehow the sun vanished this very instant, not faded, not dimmed, but disappeared completely, we wouldn't know for over 8 minutes. For that entire time the illusion would hold. The sky would remain bright. Life would go on, unaware, because the last photons from the sun would still be in transit, like a cosmic delay. The sun's farewell message would already be en route, speeding toward us at the only speed it knows. And that's true for everything we see. Our eyes don't perceive the present. They perceive delayed broadcasts of the past. The farther we look, the older the show. There's no such thing as seeing the now of the cosmos. The present is a privilege reserved for what's near. This also means that space has no universal now. Ask 2 different observers, moving at different speeds or living in different gravitational fields, what time it is, and you'll get 2 different answers. The speed of light locks time to the observer. In the realm of the cosmos, simultaneity doesn't really exist. Everything is in motion. Everything is relative. For humans, this is deeply unintuitive. We like our clocks to match. We like things to happen in order, but light doesn't care about our preferences. It moves through space the way time moves through a dream, fluid, stretched, sometimes surprising. And yet, despite all this strangeness, the speed of light is one of the most comforting constants in the universe. It never changes. It doesn't get tired. It doesn't bend the rules for anyone. No matter where you are or how fast you're moving, you'll measure light's speed as the same. It's the universe's universal truth, a glowing thread that stitches together every galaxy, every planet, every moment in time. It's also what makes the night sky so special. When you gaze at the stars, you're not just looking into space, you're looking into history. 1 billion glowing memories, twinkling, quietly, across the darkness. And whether that light took a few seconds or a few billion years to arrive, it all shares the same rule. It all travelled at the same patient, relentless pace. The speed of light doesn't just limit us, it connects us. From one edge of the cosmos to the other, across the deepest gulfs and the oldest times, it carries the stories of everything that has ever shone. And tonight some of those stories have found their way to you. If you were to ask someone how big the solar system is, they might think of the planets, all lined up like beads on a string. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. A tidy little family of worlds circling the sun, each one taking its turn. But that picture, while charming, is wildly misleading. It's not the planets that dominate the solar system. It's the empty space between them. Let's start close to home. The Moon orbits Earth at an average distance of about 384,000 kilometres. That's far enough to fit every planet between the two, with room to spare, and yet it feels familiar. We can imagine the Moon in the sky, trace its glow with our eyes, even send astronauts there and back. In cosmic terms, it's practically in our backyard. Now, the Earth-Sun distance is another story, about 150 million kilometres. That's roughly 400 times farther than the Moon. This distance is so iconic it earned its own title, 1 astronomical unit. And if you could drive to the Sun at highway speed, say 100 kilometres per hour, it would take over 170 years, without stopping. Even Mercury, the closest planet to the Sun, orbits at about 1/3 of an astronomical unit. Venus is 2/3, Earth is 1, then comes Mars at 1.5. After that, things start spreading out. Jupiter is more than 5 astronomical units away. Saturn is almost 10. By the time you reach Neptune, you're over 30 astronomical units from the Sun, and between each of these planets is a staggering amount of nothing. If you could somehow shrink the Sun down to the size of a basketball and place it in the centre of a football field, Earth would be a tiny peppercorn about 25 metres away. Neptune would be a small marble near the far edge of the stadium, and between all those tiny specks, empty seats. There's a tendency to picture the solar system as dense and busy, but it's more like a sparse desert with the occasional cactus. Most of its volume is wide, silent, and profoundly empty. Even the asteroid belt, often imagined as a cluttered junkyard of rocks, is mostly just vast space. If you were standing on an asteroid in the belt, chances are you'd see nothing else nearby. Maybe a single dot in the distance. Maybe nothing at all. But even Neptune isn't the end. Beyond the planets lies the Kuiper Belt, a frigid ring of icy debris that stretches from about 30 to 50 astronomical units. This is where Pluto lives, along with other dwarf planets like Eris, Haumea, and Makemake. Tiny, distant worlds that orbit the Sun in the twilight regions. And beyond the Kuiper Belt, the solar system keeps going. Much farther out, in a realm so remote it's almost mythical, lies the Oort cloud. We've never seen it directly, but astronomers believe it exists, a vast spherical shell of icy bodies that surrounds the solar system, possibly extending out to 100,000 astronomical units from the Sun. That's over 1.5 light years. Think about that. The Sun's gravitational influence might reach almost halfway to the nearest star, but out there, gravity is weak, objects are sparse, and time crawls. To get a real feel for the scale, consider the Voyager probes. Voyager 1 and Voyager 2 were launched in the late 1970s to study the outer planets. After their main missions ended, they kept going. Voyager 1 is now over 150 astronomical units from the Sun. It's the farthest human-made object in existence, and yet, even after more than 4 decades of travel at over 60,000 kilometers per hour, it still hasn't reached the Oort cloud. It won't get there for another few hundred years, and it may take tens of thousands of years to pass through it entirely. In a way, Voyager is our message in a bottle, a tiny piece of Earth sailing into the dark, carrying sounds and images from our world. It's a reminder of how far we've reached, and how much farther there still is. And here's something else to consider. All of this, the planets, the belts, the far-flung comets and probes, still exists in the immediate neighbourhood of the Sun. The solar system, for all its vastness, is just a tiny bubble around a single star in a galaxy filled with hundreds of billions more. It's humbling, isn't it, to realise that even within the domain of our own star, the distances are so vast they defy comprehension. And yet, we've measured them, we've mapped them, we've sent machines to the edge. What really defines the solar system isn't just the Sun or the planets, it's the silence in between, the waiting, the loneliness of space. But it's also filled with motion. Planets orbiting, comets returning, light streaming outward in all directions. Even in emptiness, there's rhythm. So how big is the solar system, really? It's as big as everything we've ever launched, everything we've ever discovered, and everything we've yet to reach. And the farther we go, the more we realise we've barely begun. The Sun feels permanent. It's always been there in the sky, rising, setting, warming our skin, lighting our days. It feels close, familiar. But when we start talking about the next nearest stars, the comforting scale of our local cosmic neighbourhood disappears. Suddenly space becomes very, very empty. The closest star to our Sun is Proxima Centauri. It's part of the Alpha Centauri system, a trio of stars bound together by gravity. Alpha Centauri A and B are both Sun-like stars, while Proxima Centauri is a faint red dwarf that orbits the other two from a much greater distance. and even though Proxima is the nearest star to us, it's still over 4 light-years away. That distance, more than 40 trillion kilometers, is so large that it almost means nothing. 4 light-years sounds manageable until you realize what light-years really represent. Light, the fastest thing in the universe, takes over 4 years just to make that trip. A spacecraft like Voyager 1, moving at more than 60,000 kilometers per hour, would take over 70,000 years to get there. And that's just the nearest star. If you could somehow scale down the solar system to something more tangible, say the Sun is the size of a marble, Earth would be a speck of dust a meter away. Neptune would be about 30 meters out. On that same scale, Proxima Centauri would be another marble over 8 kilometers away. And in between, nothing but empty space. That's what makes interstellar travel such a daunting proposition. It's not the stars themselves, it's the yawning gaps between them. Even our best engines struggle to cross the space between planets. Getting to another star is an entirely different kind of challenge. You'd need propulsion systems we haven't built yet, energy sources we haven't harnessed, and patience that spans centuries, maybe even millennia. Science fiction loves to jump between stars. Warp drives, hyperspace lanes, wormholes. It's all very exciting. But in reality, we haven't even sent a probe to another star system. There are concepts being explored, like the Breakthrough Starshot initiative, which proposes sending tiny spacecraft to Alpha Centauri using powerful ground-based lasers. These miniature probes could, in theory, reach speeds of up to 20% the speed of light and make the journey in just over 20 years. But building, launching, and aiming something that's small with that much precision is still firmly in the realm of future engineering. The truth is, the universe is mostly nothing. Stars are scattered throughout the galaxy like scattered lanterns in an endless fog. The Milky Way has hundreds of billions of stars, and yet the average distance between them is about 5 light-years. That's a whole lot of black velvet between every point of light. Let's try a more playful image. Imagine a field stretching for kilometers in every direction. In this field, you place a single grain of salt to represent the sun. Then, after walking 8 kilometers in a straight line, you place another grain to represent Proxima Centauri. Do this again and again in every direction, and eventually you'll start to get a sense of how sparsely populated space really is. A galaxy of salt, floating in a sea of emptiness. And even these grains, the stars themselves, are overwhelmingly large and powerful. Proxima Centauri is small and dim by stellar standards, but it's still about 130 times the mass of Earth. The Sun, by comparison, is over 300,000 times the mass of our planet. Each star is a giant roaring fusion engine, burning for billions of years. And yet, for all their brilliance, they remain pinpricks in a mostly invisible landscape. The emptiness between stars isn't just about physical space, it's about energy and time. Travelling these distances requires more than motion. It demands survival in the void, shielding from radiation, and communication across decades. And when you arrive, there's no guarantee that what you find will be welcoming, or even solid. That's why astronomers study exoplanets so carefully. We want to know if any of these distant stars host planets like our own. If there's another Earth orbiting Proxima Centauri, or Alpha Centauri A or B, it would be the most exciting discovery in human history. But even if there is, reaching it is another matter entirely. Yet despite these challenges, we keep trying. We keep measuring, imagining, planning. Because the stars may be distant, but they are not beyond our curiosity. And while we may not reach them with rockets anytime soon, we can still reach them with our minds. That's the strange duality of space. Physically, the stars are far beyond our grasp, but in thought, in wonder, they're already close, already part of our story, and maybe that's enough for now. To know that out there, over 40 trillion kilometers away, another star shines in our direction, that its light, dim and red, is already arriving. Not in a blaze, but in a whisper. A reminder that even in the vast quiet between the stars we're not entirely alone. If you've ever looked up at the night sky and seen that faint milky band stretching across the darkness, you've caught a glimpse of something enormous. Our home galaxy, the Milky Way. From Earth, it looks like a hazy smear of stars, too numerous and distant to resolve individually with the naked eye. But that soft ribbon of light is actually part of a massive spiral galaxy, one that contains hundreds of billions of stars, all held together by gravity and quietly spinning through space. The Milky Way is shaped like a giant flattened disk with a slight bulge in the middle. Think of a cosmic frisbee, about 100,000 light-years wide and around 1,000 light-years thick in the disk itself. That's a number so large it resists visualization. Even light, the fastest thing in existence, would need 100,000 years to cross from one side of the galaxy to the other. And nestled somewhere in that vast starry whirlpool is us, our sun, our solar system, and everything we've ever known. But we're not near the centre, where things get wild and densely packed. We live out in one of the quieter suburbs of the galaxy, about 27,000 light-years from the galactic core. It's peaceful here, relatively speaking. Our solar system is located in a minor spiral arm called the Orion Arm, sometimes also called the Orion Spur. It's a kind of galactic side street, wedged between two of the Milky Way's major spiral arms, the Sagittarius and Perseus arms. If the galaxy were a giant pinwheel, we'd be sitting somewhere between the middle and the outer edge, casually orbiting the centre at a steady pace. We're not in a particularly special spot, no galactic penthouse or downtown view. But it's quiet, stable, and that's probably one reason life had the chance to develop here. Despite being way out in the galactic suburbs, we're not standing still. The entire solar system is in motion, carried along by the rotation of the Milky Way. Right now, our sun is zipping around the galactic centre at an astonishing speed of about 828,000 kilometers per hour. That's fast enough to circle Earth more than 20 times in a single hour. But the galaxy is so vast that even at that speed, a single orbit, one galactic year, takes a very long time. In fact, it takes the Sun roughly 225 million years to make a full lap around the centre of the Milky Way. That means the last time our solar system was in this same position in the galaxy, dinosaurs were just beginning to appear on Earth. Since the Sun formed, about 4.5 billion years ago, it's only made about 20 laps around the galactic centre. 20 laps, in over 4 billion years. That gives you a sense of just how enormous this structure is. And yet, even with all this motion, the stars in the sky don't appear to shift dramatically during a human lifetime. From our tiny vantage point, the stars seem frozen. But they're not. Everything is moving, just very slowly on our timescale. If you had a time-lapse that ran for millions of years, you'd see stars whirling around like fireflies in a slow, graceful dance, tracing out the spiral arms of the galaxy as they orbit. The centre of the Milky Way is a very different place from where we are. There, stars are packed tightly together, orbiting a mysterious and massive object, a supermassive black hole known as Sagittarius A star. It has a mass of about 4 million suns, and sits like a quiet anchor at the galaxy's core. We can't see it directly, but we can observe its gravitational effects on nearby stars, which whip around it at breathtaking speeds. Meanwhile, out here in the Orion Arm, things are more relaxed. Stars are more spread out. There's room for planets to orbit, for solar systems to remain undisturbed, and for life to quietly evolve over billions of years. It's almost as if we lucked out with our real estate. What's even more remarkable is that everything we can see with the naked eye in the night sky, every star you've ever wished upon, is within just a few thousand light-years of Earth. That's only a tiny sliver of the Milky Way's full span. The vast majority of the galaxy remains out of sight, hidden by distance, dust, or simply too dim to see. Yet, we know it's there. Radio telescopes and infrared surveys have helped map out its spiral arms, trace the movement of its stars, and even reveal the ghostly halo of dark matter that surrounds it all. Sometimes it's tempting to think of our galaxy as just a backdrop, a pretty stretch of sky. But it's more than that. The Milky Way is our island in the cosmic ocean. It's the only galaxy we've ever known from the inside. Every single thing humanity has ever done, every civilization, every idea, every sunrise and every song has happened on a speck of rock orbiting a star that's quietly circling a galaxy we can barely comprehend. And we're still moving, still riding the spiral, still drifting around the centre like leaves in a gentle current. No matter how still the night may seem, you're travelling through the galaxy at hundreds of thousands of kilometres per hour on a journey that's been going for billions of years and shows no sign of stopping. That's our place in the Milky Way. Not central, not special, but not insignificant either. Just part of something ancient and beautiful, spinning slowly in the dark. When we gaze up at the night sky, it's easy to imagine that stars are scattered randomly across the cosmos, each one shining alone in the void. But in reality, stars often form together in groups. Families born from the same clouds of gas and dust, bound by gravity and shared origins. These stellar gatherings come in many forms, and each tells a different story about the life of stars and the architecture of the galaxy. Let's begin with the open clusters. These are loose associations of stars, typically a few hundred to a few thousand, born from the same giant molecular cloud. They're young, relatively speaking, often only a few million to a few billion years old. Because they haven't had time to drift too far apart, their members are still loosely bound by gravity. Open clusters are like star nurseries, just out of the cradle. One of the most famous examples is the Pleiades, also known as the Seven Sisters. On a clear night you can spot them without a telescope, a tight shimmering group of stars clustered in the constellation Taurus. The Pleiades are only about 100 million years old, practically infants in stellar terms, and they still shine with youthful blue glow. They're a beautiful reminder that stars are often born in batches, not in isolation. Then there are globular clusters, very different creatures. These are dense, spherical collections of stars, often numbering in the hundreds of thousands or even millions. Unlike open clusters, globular clusters are ancient. Some are over 12 billion years old, nearly as old as the galaxy itself. They orbit the Milky Way in a sort of halo, outside the main galactic disk, like cosmic bees swarming around a hive. Globular clusters are tightly packed, with stars crammed so close together that a single telescope image might show thousands of points of light all glowing in a compact sphere. One of the most famous is M13, the Great Hercules Cluster. It's about 25,000 light-years away and contains over 300,000 stars. If you lived on a planet within such a cluster, your night sky would be ablaze with starlight, far brighter and more crowded than anything we see from Earth. Beyond the star clusters, we find the nebulae, those hazy, colourful clouds scattered throughout the galaxy. The word nebula comes from the Latin for cloud, and that's exactly what they are. Massive clouds of gas and dust, often spanning dozens or even hundreds of light-years. They're the raw material from which stars are born, and sometimes the remnants of stars that have died. Perhaps the most iconic is the Orion Nebula, visible even with a small telescope and located just below Orion's belt in the night sky. It's about 1,300 light-years away, and is part of a much larger region of star formation known as the Orion Molecular Cloud Complex. Inside the nebula, new stars are forming even now, glowing and heating the gas around them into a luminous swirl of reds, blues and purples. It's one of the closest and most studied stellar nurseries, a place where the next generation of suns is quietly flickering into existence. Then there's the Eagle Nebula, home to the famous pillars of creation, towering columns of gas and dust captured in a stunning image by the Hubble Space Telescope. These structures are vast. Each pillar is several light-years tall, but they also serve as cradles of starbirth. Inside them, dense knots of material are collapsing under gravity to form new stars, hidden from view by the thick clouds surrounding them. What's truly astonishing is how small even these magnificent structures are on the scale of the galaxy. A typical nebula might stretch for a few dozen light years. A large one, maybe a few hundred. But the Milky Way is 100,000 light years wide. That means a sprawling nebula like the Orion, or the Carina, full of glowing gas, star formation and brilliant colour, is just a tiny smudge on a galactic map. A dust mote in the spiral arm. Even the largest star clusters are just points of light when seen from far enough away. They may contain thousands or millions of stars, but they vanish into insignificance compared to the sheer vastness of the galaxy. If the Milky Way were a giant canvas, these clusters and nebulae would be delicate brushstrokes, tiny flourishes barely noticeable at a distance. And yet within these brushstrokes entire dramas unfold. Stars are born, shine for billions of years, and die in spectacular explosions. Planets form from the surrounding debris, moons collide and coalesce. Life may even begin on some quiet, watery world orbiting a young sun. It's humbling to realise that every speck of light we see in the sky, every glowing dot in a cluster or flickering swirl in a nebula, might be the backdrop to entire histories we can barely imagine. Stellar neighbourhoods are more than just a collection of stars. They're shaped by gravity, by time, and by the laws of physics. Stars that are born together may eventually drift apart, pulled by the motions of the galaxy. But while they're close, they share more than just space. They share chemistry, age, and movement, a kind of cosmic kinship. Astronomers study these clusters to learn about stellar evolution. By observing stars at different stages of their lives, but with similar ages and compositions, we get a clearer picture of how stars grow, change, and eventually die. And by studying the light from nebulae, we can trace the ingredients that go into making stars, and even the elements that make up planets, oceans, and us. These local groupings of stars scattered across the galaxy like glitter spilled on velvet are among the most beautiful features of the cosmos. They're the places where stars are born, where they gather, and where they end. Quiet neighbourhoods in a galaxy that never sleeps. And while they may be just tiny features on the face of the Milky Way, they're also where everything begins. In the soft glow of a nebula, or the dense core of a cluster, the universe is busy writing its next chapter, one star at a time. For a long time, we looked up at the night sky and thought we were seeing everything. Stars, planets, maybe a few wispy clouds of gas, and the occasional fuzzy patch that might have been a distant nebula. The Milky Way, stretching across the sky, seemed like the grand total of the cosmos. But then, with better instruments and more patient eyes, we discovered something astonishing. We weren't looking at everything, not even close. One of the most famous moments in observational astronomy came in the mid-1990s, when the Hubble Space Telescope was pointed at what looked like an empty patch of sky. Not bright region, not a well-known constellation, just a tiny, dark corner of space, no bigger than a grain of sand held at arm's length, and Hubble just stared at it. For over 10 days it gathered light from that small, silent patch. Many people expected it to find almost nothing. What it found changed our understanding of the universe forever. The image that came back was the Hubble Deep Field, and instead of darkness, it revealed a canvas brimming with light. Thousands of galaxies, each one unique, each one packed with stars. Spiral galaxies, elliptical galaxies, irregular smudges, glowing cores, delicate arms. They filled the frame like glitter flung across velvet. Not stars, not planets, galaxies. Each one home to billions or even trillions of stars, each one unimaginably far away. And remember, this was just one tiny speck of the sky. A pinpoint, a fraction. If a single Hubble Deep Field could contain thousands of galaxies, then how many more might be hiding across the full sweep of the cosmos? That question led astronomers to try a rough estimate. They scaled up from what they could see in that tiny window, extrapolating based on similar deep field observations. The result? An estimate that there are around 2 trillion galaxies in the observable universe. That's 2 trillion islands of stars, each with their own solar systems, clouds of gas, black holes and mysteries. But here's the twist. Most of those galaxies are invisible to us. Even with powerful telescopes, the light from the farthest galaxies is too faint, too stretched by cosmic expansion, or too obscured by dust to reach us in detail. The universe is full of hidden things, not because they don't exist, but because we're too limited to see them clearly. It's a bit like trying to understand the ocean by staring at a single drop of water. There's depth there, movement, life, but it's just a sample of something far vaster and more complex. With galaxies, the same principle applies. What we see is only a tiny fraction of what's truly out there, and yet the fact that we can see anything at all is incredible. These galaxies are unimaginably far away. Some of the light reaching us began its journey billions of years ago. It has crossed the expanding void of space, stretched into longer and redder wavelengths as the universe swelled around it, and finally arrived here, at our tiny planet, around our unremarkable star, filtered through the lenses of telescopes we placed into orbit. It's worth pausing on that for a moment. Every galaxy we see in those deep field images is not just far away, it's also old. We're seeing them as they were, not as they are. Some of them may not even exist anymore. They could have collided, merged, burned out, or changed beyond recognition. But their light is still on the way, still crossing the gap, still whispering their ancient stories to whoever is listening. And that's just the observable universe, the part of the cosmos whose light has had time to reach us since the Big Bang. There may be more beyond that horizon, a lot more, entire regions of space too distant for their light to have arrived yet, or possibly forever unreachable due to the accelerating expansion of the universe. Which raises an intriguing and humbling question. Are we surrounded by galaxies we'll never see? The answer is very likely yes. The universe is expanding, and not just in the usual sense of things moving away. It's the very fabric of space itself that's stretching, carrying galaxies along like raisins in a rising loaf of bread. And the farther away something is, the faster it appears to move from us. At a certain distance, about 14 billion light years, that movement becomes faster than the speed of light, not because the galaxies themselves are zooming through space, but because space itself is expanding between us and them. This means that some galaxies are already beyond our reach. Their light, no matter how long we wait, will never make it to us. They've slipped past the cosmic event horizon. It's as though the universe is drawing the curtains quietly and inevitably on parts of itself. But even within our observable bubble, the number of galaxies is staggering. Each one has its own structure, its own population of stars, its own orbiting worlds. Some are small and dim, containing only a few billion stars. Others are giants, sprawling, luminous behemoths, with hundreds of billions of suns lighting up their spiral arms or elliptical contours. It's hard to wrap the mind around such numbers. 2 trillion galaxies, each one holding hundreds of billions of stars. Multiply that out, and you get something like 200 sextillion stars. That's a 2 followed by 23 zeros, and that's not counting the stars we can't yet detect, or the ones that have already gone dark. And yet, from Earth, without a telescope, you can see only a few thousand stars with the naked eye. No galaxies, aside from the faint blur of the Andromeda Galaxy, and maybe the Magellanic Clouds if you're in the southern hemisphere. The rest remain hidden, waiting behind the veil of distance and darkness. It's almost comical. We live in a universe that's utterly packed with galaxies, and yet most of them are invisible, unreachable, unknowable. We drift in a cosmic sea surrounded by luminous islands, and we can only glimpse the nearest waves. But there's beauty in that limitation, because every galaxy we do see becomes more precious. A single deep field image becomes a cathedral of light, a reminder of just how much is out there and how little we need to feel wonder. We may never see them all. We may never map every distant spiral or chase down the faintest glimmers from the edge of time. but we can imagine them. We can know they're there, and sometimes that knowledge is enough to stir something deep inside us. Because somewhere, far beyond what any telescope can reach, another galaxy spins slowly in the dark, and though its light may never find us, it still shines. When we talk about neighbourhoods, we usually mean a few houses, maybe a couple of streets, a community you can walk across on a lazy evening. But in cosmic terms, our neighbourhood, the local group, is something quite different. It's a gravitational family of galaxies, stretching millions of light years across, held loosely together by the quiet tug of gravity. The local group contains about 50 galaxies, although that number can vary a little depending on how you define a galaxy and whether you count the faintest ones. Most of these aren't grand spirals or luminous giants. They're small, irregular dwarf galaxies, faint collections of stars orbiting larger neighbours like tiny moons. But there are a few standouts, and two in particular dominate the group: our own Milky Way and the Andromeda Galaxy. The Milky Way is massive, containing somewhere between 200 billion and 400 billion stars, but Andromeda, also known as M31, is even larger. It's the heavyweight of the local group, with perhaps 1 trillion stars and a more defined spiral structure. It lies about 2.5 million light-years away, which in galactic terms is quite close, practically next door. Andromeda is visible to the naked eye under dark skies, though it appears only as a faint smudge. It's amazing to think that when you're looking at it, you're seeing the light from a galaxy that's been travelling toward us for over 2 million years. And what's even more extraordinary is that this quiet, distant smudge is on a collision course with us. That's right. Andromeda and the Milky Way are slowly drifting together, pulled by their mutual gravitational attraction. Despite the expansion of the universe, local gravity can still bring galaxies together, and our two spirals are currently closing the gap at a speed of around 110 kilometers per second. In about 4 billion years, they'll collide. But this isn't a crash in the usual sense. Galaxies are mostly empty space, so when they merge, stars won't slam into each other like bumper cars. Instead, they'll pass through like ghosts, influenced only by gravity. Over time, their shapes will distort, their stars will intermingle, and what remains will likely be a giant elliptical galaxy, sometimes called Milkomeda, a blend of their names. It will be a whole new kind of home. For now, though, both galaxies remain distinct and each has a retinue of smaller satellites. The Milky Way alone has dozens. The two most famous are the Large and Small Magellanic Clouds, irregular dwarf galaxies visible from the southern hemisphere. They orbit our galaxy in loose looping paths and are among the few galaxies visible without a telescope. There's also the Sagittarius dwarf galaxy, which is currently being slowly shredded and absorbed by the Milky Way. These smaller galaxies are pulled and twisted by the gravity of their larger host, their stars slowly stretched into streams that wrap around the galactic disk. It's a bit like cosmic recycling. The galaxy grows by swallowing its neighbours, and Andromeda has its own satellites too, galaxies like M32 and M110, which orbit close to its spiral arms. Some of these are likely to be consumed in the distant future, adding their stars to Andromeda's already enormous population. Across the local group, these gravitational relationships define the structure. It's not a cluster in the dense, packed sense you might find elsewhere in the universe. The galaxies here are spread out, with vast distances between them, but they're still linked, quietly orbiting a shared centre of mass, like dancers slowly circling an invisible point. Between the galaxies lies an intergalactic medium, thin, tenuous gas and dark matter that stretches through the void. We can't see most of it directly, but its presence is felt through gravity, and it's this invisible web that shapes the motion of the local group, guiding galaxies as they drift and interact over billions of years. Astronomers believe the local group is part of a larger structure known as the Virgo supercluster, which itself is a small piece of an even grander web called Laniakea. But here in our quiet corner, things are relatively peaceful. There are no massive collisions happening at the moment, just slow, steady movement. an ancient gravitational ballet playing out across millions of light years. One interesting feature of the local group is that many of its dwarf galaxies are hard to spot. They're faint, low in mass, and easily lost against the background. Some of them have only a few million stars, tiny in galactic terms, and are often discovered through careful analysis of star motions or subtle fluctuations in the sky's brightness. As our telescopes become more sensitive, we keep finding new members of this quiet neighbourhood. What's also fascinating is how these small galaxies might play a bigger role than they appear. Some scientists think that dwarf galaxies could be the building blocks of larger ones, that the Milky Way and Andromeda grew in part by consuming galaxies like these. Their dark matter halos, star populations and chemical compositions all offer clues to the grand puzzle of galaxy formation. Even more humbling is the realization that most of these galaxies are ancient. They've been drifting here for billions of years, slowly evolving, occasionally colliding, often just existing in silence. Long before Earth formed, the local group was already in motion, and long after our planet is gone, its members will still be orbiting, merging and glowing quietly in the darkness. When we imagine the universe, it's tempting to focus on the biggest structures, the galaxy clusters, the filaments, the deep cosmic web. But there's something beautiful about starting with our own little corner. The local group may be just one of many such families scattered across the universe, but it's ours. It's the one we know from the inside. 50 galaxies, give or take, 2 major spirals, dozens of dwarfs, countless stars drifting together through the quiet night. It's not a bustling city, more like a remote village, where each galaxy moves at its own pace, influenced by the slow, patient pull of gravity. Not crowded, not empty, just enough to feel like we're not completely alone in this vast cosmic landscape. And when you look up at the stars, you're not just seeing points of light, you're seeing part of a bigger structure, part of a larger community, a gravitational neighbourhood filled with ancient neighbours, each with their own story to tell. If galaxies were cities, then superclusters would be continents, vast regions of the universe containing not just 1 or 2 galaxies, but tens of thousands of them, organised into sprawling clusters connected by delicate threads of matter. These aren't random piles of stars drifting through space. They're structured, they form patterns, and those patterns are among the grandest in the entire cosmos. Our own Milky Way, along with the entire local group of galaxies, is part of something much larger, the Laniakea supercluster. The name comes from Hawaiian and means immense heaven. It's a fitting title because this structure stretches over 500 million light years and contains more than 100,000 galaxies. It's hard to fathom what that really means. 500 million light years, light, the fastest thing in existence, would still need 500 million years to travel from one side of this structure to the other. But even Laniakea isn't a standalone island in space. It's one part of an interconnected web that stretches across the entire observable universe. This is the cosmic web, a vast filamentary structure made of galaxies, gas, dark matter, and gravity. When astronomers simulate the large-scale structure of the universe using supercomputers, the result looks like a 3-dimensional spiderweb. Galaxies and clusters form the dense intersections, or nodes, while vast filaments connect them like glowing bridges. In between, there are enormous voids, regions where hardly anything exists at all. These voids aren't just empty in a casual sense. They can span hundreds of millions of light years and contain almost no galaxies at all. They're like black ink between strokes of paint, vast cosmic deserts surrounded by luminous cities. And while the voids look like nothing, they play a key role in the shape and evolution of the universe. Their emptiness helps define where matter gathers and where it does not. The structure of the cosmic web didn't appear out of nowhere. It began with tiny fluctuations in the density of matter just after the Big Bang. Over billions of years, gravity amplified those differences. Regions that were slightly more dense attracted more material, growing into filaments and clusters, while less dense areas expanded into voids. The result is a cosmic landscape shaped by the relentless tug of gravity and the passage of time. What's fascinating is how these structures resemble fractals, complex patterns that look similar at different scales. Zoom in, and you find galaxies forming clusters. Zoom out, and those clusters form superclusters. Zoom further, and superclusters connect through filaments, all the way up to the larger scales we can observe. Each level reflects the one before, not identically, but with a kind of self-similarity that feels poetic. The universe repeats itself in complexity, from stars to galaxies to networks of galaxies spanning billions of light years. In 2003, astronomers identified one of the largest known structures in the universe, the Sloan Great Wall. It spans over 1.3 billion light-years across and contains several galaxy superclusters linked together. Later discoveries, like the Hercules Corona Borealis Great Wall, have challenged even that scale, suggesting the existence of structures so large they almost defy our current understanding of cosmology. And yet, these enormous structures are still just part of the observable universe. There may be even more beyond what we can see. Regions of the cosmic web whose light hasn't had time to reach us yet. The web might stretch on forever, or it might be part of a larger pattern we don't yet understand. From our position inside a galaxy, it's difficult to fully grasp these scales. We live on a planet orbiting a star, which is just one of hundreds of billions in the Milky Way. Our galaxy is part of a small group, which sits within Laniakea, which is only one part of the web, and all of this is woven together across space like threads in an ancient tapestry, one still being spun. What's even more incredible is that we've mapped this web using the light of galaxies that are billions of years old. By measuring the redshift of thousands, even millions of galaxies, astronomers have created three-dimensional maps of cosmic structure. These maps show where galaxies cluster, where they string into filaments, and where the dark patches lie. In a way, it's like taking a picture of the universe's skeleton. The luminous matter, stars, gas, and galaxies, traces out the hidden shape of something bigger, something invisible. Most of the mass in the universe doesn't shine. It's dark matter which neither emits nor absorbs light, but whose gravitational influence reveals its presence. The cosmic web is really a map of dark matter first, and ordinary matter second. We're seeing the scaffolding on which the universe was built. When we zoom out far enough, the details begin to fade, individual galaxies blur together, clusters become dots, the filaments stretch thin, and eventually we hit a limit. Not just in terms of resolution, but in meaning. At some scale, the universe becomes statistically uniform. No more structure, no more web, just a smooth field of energy and matter, evenly distributed. This is what cosmologists call the cosmological principle, that on the larger scales the universe looks the same in every direction. It's not a featureless void, but a balanced whole. Still, it's a humbling thing to consider, that we are a tiny part of a galaxy, in a quiet suburb of a vast web, stretching across space like veins in a living organism, a universe with texture and flow, a place where gravity and time have drawn invisible lines, guiding the motion of galaxies over billions of years. And yet, we're not outside observers, we're inside it, we're woven into the web. Every atom in your body was once part of a star, and every star is part of a galaxy, and every galaxy is moving along the threads of the cosmic structure, responding to forces that were set in motion at the dawn of time. You are, in a very real sense, connected to everything, to the stars in other galaxies, to the light from other times, to the great cosmic architecture that hums beneath the surface of the visible sky. It's easy to feel small when you think about superclusters and cosmic webs, but maybe it's better to feel included, to realize that we belong to something enormous, not as outsiders looking in, but as participants in a grand unfolding pattern. Zoom out far enough and the universe becomes a blur. But just before it does, it reveals something profound. a hidden order, delicate and vast, stitched together across time and space, a structure that tells a story far larger than any one galaxy, yet one we're a part of all the same. The universe, as far as we can tell, doesn't come with walls. There's no giant do not enter sign at the edge, no curtain we can pull back to see what's behind it. And yet, there is a limit to what we can see. It's not a hard boundary in space, it's a limit in time. A horizon drawn not by what exists, but by what light has had time to reach us. We call it the observable universe, and it stretches about 93 billion light years across. That's a huge number, bigger than big. But it's not the size of the entire universe, only the part we can see. Like standing on a mountaintop and looking out at the horizon, the visible edge is defined not by what's there, but by what's within reach. To understand why there's a limit at all, we have to think about light. Light doesn't travel instantly. It takes time to move through space. And since the universe is about 13.8 billion years old, you might think the most distant thing we could possibly see would be 13.8 billion light years away. That would make sense if space weren't expanding. But space is expanding. It has been ever since the Big Bang, and not in a gentle, cruising along sort of way. The expansion has been accelerating. That means the light we see from distant galaxies was emitted long ago when those galaxies were much closer. But as the light made its long journey toward us, space itself stretched, dragging the light waves along with it. By the time they arrived, those galaxies had moved even farther away. Because of this cosmic stretching, the light from the most distant visible objects comes from galaxies that are now over 46 billion light years away. Double that distance, and you get the full diameter of the observable universe, roughly 93 billion light years, give or take a few hundred million. So even though the universe is 13.8 billion years old, the observable universe is much, much larger. It's like shining a flashlight across an inflating balloon. Except the beam stretches, the surface expands beneath it, and by the time it arrives, everything's moved apart. This might sound a bit mind-bending, and that's because it is. Our instincts are good at dealing with apples, ladders, and traffic lights, not with space that bends and stretches like warm taffy. But the math checks out, and the telescopes confirm it. We can see galaxies whose light began its journey billions of years ago, long before Earth formed. Some of these ancient galaxies are so faint and redshifted that they're barely detectable. They appear as smudges, ghosts of the past floating at the edge of vision. But beyond them, darkness. Not because there's nothing there, but because the light from those places hasn't had time to reach us, and it may never arrive. This is one of the strangest truths about living in an expanding universe. There are parts of the cosmos that we will never see, no matter how long we wait. Their light is too far away, the expansion too fast. They exist beyond the cosmological event horizon, the limit beyond which information simply cannot travel to us, even at the speed of light. This doesn't mean those places are empty. In fact, they might be bustling with galaxies, stars, and civilizations. But for us, they're permanently invisible, trapped beyond the reach of light, behind the curtain of cosmic acceleration. It's worth noting that the observable universe is centered on us, but not because we're special. It's centered on us simply because we're the ones doing the observing. Any other observer in a different galaxy would see their own observable universe, also roughly 93 billion light years across, also centered on their position. And while there would be some overlap, the outer regions would differ. Each galaxy, each planet, each patch of sky has its own personal slice of the visible cosmos. So when we say the observable universe, we're not describing a box or a bubble floating in space. We're describing a sphere of visibility, our cosmic field of view, shaped by the age of light and the rules of relativity. Inside that sphere we see a lot. Galaxies arranged in clusters and filaments, supernovae flashing in the distant past, quasars blazing from the centers of young galaxies. We can even detect the afterglow of the Big Bang itself, the cosmic microwave background radiation, which comes from a time just 380,000 years after the universe began. That light has been travelling ever since, carrying the imprint of the universe's earlier structure. But there are limits to what we know. Beyond a certain point, galaxies are too far and faint to observe. Their light is red-shifted beyond detection. Some lie behind thick clouds of intergalactic dust. Others are simply blocked by the age of the universe. They haven't had enough time to send their light our way. And then there are the philosophical questions. If we can't see it, does it count? Is the unobservable universe just as real as the part we can see? Most cosmologists believe it is. The laws of physics don't suddenly change beyond our line of sight. The universe almost certainly continues beyond the horizon. It might be infinite, it might curve back on itself, or it might lead into something else entirely. But for now we work with what we can observe. 93 billion light-years of data, arranged in a glowing, swirling, expanding tapestry of stars and galaxies. It's more than enough to keep our minds busy. And here's something comforting. Within that bubble, we've learned a great deal. We've mapped the distribution of galaxies, measured the expansion rate of space, estimated the amount of dark matter and dark energy, and reconstructed the early moments of cosmic history. We've sent telescopes to orbit, peered into the deepest parts of space, and captured light that began its journey before our planet existed. Even though the observable universe is only a fraction of the whole, it's an astonishing fraction. It holds the fingerprints of time, the echoes of ancient starlight, and the blueprint of everything we know. Beyond that, there may be more, much more. Perhaps other regions with different physical constants. Perhaps copies of our galaxy. Perhaps things so strange we wouldn't even recognize them. But whatever lies beyond the observable edge, it is for now hidden behind the simple barrier of time. And that's the quiet wonder of the observable universe. It's not the edge of reality, just the edge of our sight. A softly glowing horizon, always receding, always just out of reach. Not a limit to what is, but a reminder of how far light can travel, and how far we've come to meet it. There's a cosmic horizon around us, not made of walls or clouds, but of time and light. A soft boundary where the light from beyond simply hasn't had the chance to arrive yet. That boundary defines what we call the observable universe, a sphere stretching roughly 46 billion light-years in every direction. But what lies beyond it? That question leads us into the heart of mystery. Because if we can only observe what light has had time to reach us, then the rest of the universe, the unobservable universe, could be vast beyond comprehension. And we may never, ever see it. Our story starts in the earliest moments of time. Right after the Big Bang, within the first fraction of a second, the universe went through a period known as cosmic inflation. This was not a gentle swelling or a steady breeze through the cosmos. This was an explosion of expansion, unimaginably fast and mind-bendingly brief. In less than a trillionth of a second, space itself expanded faster than the speed of light, stretching quantum fluctuations into macroscopic structures that would later form galaxies and stars. Inflation solved a few stubborn problems in cosmology, like why the universe appears so smooth on large scales, and why it looks flat instead of curved. But it also planted the seeds of the cosmic web we see today. Those tiny ripples, expanded and frozen by inflation, became the blueprint for everything. Gravity pulled them together, and over billions of years, stars lit up where fluctuations once drifted. And when the universe cooled enough for light to travel freely, about 380,000 years after the Big Bang, we were left with a soft, glowing afterglow. That glow still surrounds us today. It's called the cosmic microwave background, or CMB for short, and it's the oldest light we can see. But it's not the oldest thing that exists. It's just the oldest light that's had time to reach us. And that brings us back to the horizon. Everything beyond that glow, everything farther than that ancient light, exists in darkness, not because it isn't real, but because we haven't received its message. And thanks to the ongoing expansion of space, some of those messages never will arrive. They're too far, the space between us growing too quickly. The light is on its way, but the road is stretching faster than the traveller can run. It's like standing at the shore and watching a ship disappear into the mist. You know there's more ocean beyond, but you can't see it, and no matter how hard you squint, the ship stays hidden. Not because it doesn't exist, but because the light it reflects will never reach you. So what's out there? What lies beyond the cosmic horizon? One possibility, perhaps the simplest, is that the universe continues more or less as it does here. More galaxies, more stars, more clusters and voids, an endless quilt of matter and energy stretching in every direction. If the laws of physics are the same everywhere, there's no reason to think our region is particularly special. The unobservable universe may be unimaginably large, but also rather familiar. In fact, many cosmologists believe the universe is either extremely large or truly infinite. If that's the case, then our observable universe is just a single bubble in an ocean of space, one tiny patch of a much larger whole. You could travel in a straight line forever and never find a wall. There would be no edge, just more and more space. In such a scenario, every possibility allowed by physics could be realized somewhere. There might even be regions where matter is arranged in the exact same pattern as here, not because of magic or parallel dimensions, but simply because, given enough space, repetition becomes inevitable. Some theories suggest that statistically, there could be another patch of universe identical to ours located about 10 to the power of 10 to the power of 118 meters away. That's a one followed by a number so large it's almost silly to write down. Of course, this doesn't mean that such places are accessible. Even if the universe is infinite, most of it is permanently out of reach. The expansion of space has already ensured that some galaxies have slipped beyond the event horizon. Their light is lost to us. Their history, their stars, and any civilizations they might contain are effectively erased from our future. It's a bit like living in a snow globe. We can look around and see the glittering flakes of nearby galaxies. We can measure their distances, trace their motion, and peer backward in time. But beyond the curve of the glass, things blur. Not because they don't exist, but because the light simply hasn't made it through. And just beyond that glass, there may be realms where the rules are different. Some models of inflation suggest that our universe is just one pocket among many, a bubble in a vast multiverse. In this picture, different bubbles could have different physical constants, different particles, even different numbers of spatial dimensions. Some might be utterly inhospitable to life. Others might be stranger than anything we can imagine. If inflation happened once, it could have happened again and again, sprouting an endless foam of universes. But here's the tricky part. These ideas, while mathematically consistent, are hard, perhaps impossible, to test. By definition, the unobservable universe is beyond our reach. We can make educated guesses based on theory and indirect evidence, but we may never get definitive answers. It's like hearing a sound behind a locked door and trying to guess what's making it. You might come up with plausible explanations, but unless the door opens, they remain just that, guesses. Still, even uncertainty has value. It reminds us of the limits of our perception and the humility of our place in the cosmos. We've come a long way in understanding the universe, from the earliest moments of the Big Bang to the large-scale structure we see today. But there will always be more that we cannot reach, more that stretches into darkness, and perhaps that's part of the beauty. The cosmos is not a puzzle to be fully solved, but a mystery to be lived with, a story that unfolds only so far before fading into silence. The unobservable universe isn't a flaw in our understanding. It's a feature of the universe itself, a vast, unknowable expanse that sits just beyond the edge of light. And though we may never see it, we are part of it. We're made of the same matter, shaped by the same physics, drifting in the same ocean of space. We'll always be curious. We'll always wonder. That's what makes us explorers. And even if we never cross that final horizon, it won't stop us from looking up, searching the sky for faint signals, ancient echoes and distant lights that whisper from just beyond the edge of sight. At first glance, it's easy to imagine galaxies as objects floating in space, each one speeding away like cosmic ships sailing through a dark ocean. That's certainly how it feels when we look at deep space images, clusters drifting apart, spiral arms twirling quietly, galaxies caught in the slow ballet of cosmic motion. But that picture, while tempting, isn't quite right. The galaxies aren't simply moving through space. What's really happening is far stranger. Space itself is stretching. This concept, the expansion of space, is one of the most counterintuitive and beautiful ideas in cosmology. It means that galaxies aren't pushing their way through some pre-existing void. Instead, the fabric of space between them is expanding. The galaxies are being carried apart not by their own motion, but by the growth of the space that surrounds them. They're not swimming through the water, they're embedded in the water, and the water itself is rising. The story of this discovery begins with one of the most important astronomers of the 20th century, Edwin Hubble. In the 1920s, Hubble was observing galaxies through the 100-inch telescope at Mount Wilson Observatory in California. At the time, astronomers were just beginning to understand that the faint fuzzy patches in the night sky weren't clouds of gas within the Milky Way. They were entire galaxies, filled with billions of stars and incredibly far away. Hubble measured the light from these galaxies and noticed something unexpected. The light was stretched, shifted toward the red end of the spectrum. This red shift wasn't a one-off. It appeared consistently, and it increased with distance. The farther away the galaxy, the redder its light. This was a huge clue. When light waves stretch out like that, it usually means the source is moving away. Think of the Doppler effect, where the sound of a passing car drops in pitch as it speeds away. The same thing happens with light. If a galaxy is racing away from us, its light gets stretched, reddened, elongated. But Hubble saw more than just movement. He saw a pattern. The farther away a galaxy was, the faster it seemed to be receding. This relationship became known as Hubble's law, and it was the first solid evidence that the universe itself was expanding. But again, this wasn't just about motion. Over time, physicists realized it wasn't that galaxies were racing outward like sparks from a firework. It was the space between them that was expanding. The galaxies were mostly standing still, like raisins in a loaf of bread as it rises. The raisins don't move much on their own, but the dough between them grows, pushing them apart. This model of cosmic expansion became one of the cornerstones of modern cosmology, and it leads to some strange consequences. For one, it means that over time galaxies will move farther and farther apart, not because they're choosing to, but because the universe is still expanding, and that expansion is accelerating. A mysterious force known as dark energy is driving this acceleration, causing space to stretch faster and faster. No one fully understands what dark energy is, but we can see its effects. Galaxies that were once faint smudges are now disappearing beyond the edge of visibility. The light they emit gets stretched so much that it fades into darkness, redshifted beyond what we can detect. In the very distant future, entire galaxies will slip beyond our cosmic event horizon. Their light will never reach us again. They'll still exist, but for all practical purposes, they will vanish from our view. Not because they've gone anywhere, but because the space between us has grown too wide, too quickly. This leads to a sobering thought. Right now, we can see millions of galaxies scattered across the night sky. But as the universe continues to expand, most of those galaxies will fade away. In tens of billions of years, an observer in the Milky Way, or what remains of it, might look up and see only a handful of nearby galaxies. All others will be gone from the sky, their light lost forever. It's a strange fate. The universe started as a dense hot soup of particles, all tightly packed together. Then it expanded, cooled, and structured itself into galaxies, stars, and planets, and now It's stretching so fast that most of those galaxies will eventually drift into invisibility. In a way, the cosmos is pulling itself apart, not violently, but gently, inevitably. Yet the beauty of this story lies not just in its scale, but in how we discovered it. Through a careful study of light, from humble mountaintop observatories to powerful space telescopes, we figured out that the universe is growing, not just in space, but in understanding. It's worth noting that this expansion doesn't affect everything equally. Galaxies like the Milky Way are held together by gravity. The stars inside don't drift apart because the gravitational pull is stronger than the expansion. Even galaxies within the same local group, like Andromeda and the Milky Way, are bound tightly enough to resist the cosmic stretch. In fact, we're on a collision course with Andromeda, due to collide in about 4 billion years, so the expansion isn't something you'd notice on a local scale. It only becomes apparent when you zoom out, way out, and look across millions of light years. But once you do, the effect is undeniable. Space is growing, not into anything. There's no outside to expand into. Space is just becoming more space, and it's taking everything with it. This also helps explain why the night sky is dark. It's not that there aren't enough stars, it's that the light from most of them has been redshifted into oblivion. Over time, the expansion of the universe has dimmed the cosmic backdrop, stretched the starlight and scattered the galaxies like seeds on the wind. Still, despite all this movement, we remain connected to the universe through light. The photons we collect from distant galaxies are ancient travellers, stretched by time and distance, but still able to tell us their story. They whisper of a cosmos in motion, of clusters forming, of stars burning, of galaxies drifting quietly apart. And while the expansion leads to isolation over unimaginable spans of time, it also brings perspective. It reminds us that nothing stays still, not even space itself, that the universe is a living, changing place, with a history and a future as vast as its stars. The idea that space is stretching might feel unsettling at first, but in another way it's oddly poetic. Everything is moving, not because it wants to escape, but because the universe itself is making room. Room for time to pass. Room for galaxies to breathe. Room for light to travel, and for us to catch just a glimpse of it, before it fades into the expanding night. Light, as we experience it on Earth, seems simple. It turns on, it turns off, it travels straight, it bounces off surfaces. But when it comes to the cosmos, light is more than just brightness. It's time, it's motion, it's history itself, stretched across space, revealing truths not just about where things are, but when they were. And central to this cosmic storytelling is redshift. Imagine for a moment the sound of a passing ambulance. As it approaches, the siren's pitch is high. As it passes and moves away, the pitch drops. This is the Doppler effect. The same thing happens with light. When something moves toward you, its light shifts toward the blue end of the spectrum, shorter wavelengths. When it moves away, the light shifts toward the red, longer wavelengths, hence redshift. But there's a twist. In space, this redshift isn't always caused by objects moving in the usual way. Often, the redshift we observe is due to the expansion of space itself. It's not that distant galaxies are fleeing from us like startled birds. It's that the space between us and those galaxies is growing, stretching the light as it travels. Think of light as a wave, riding through the ocean of the universe. As the space beneath it expands, the wave stretches out. Its crest and trough grow farther apart. The colour changes. What might have been a vibrant blue becomes a soft red. Over billions of years, that stretch adds up. A beam of light emitted when the universe was young arrives looking completely different. This is redshift, and it's not just a curious phenomenon, it's a ruler. It tells us how far a galaxy is, and more importantly, how long its light has been travelling. Because when we look at galaxies, we don't see them as they are now. We see them as they were. Light from the Andromeda galaxy takes over 2 million years to reach us. That's 2 million years of cosmic time frozen in every photon. When you look up at Andromeda, you're looking into the past. The farther out we gaze, the farther back in time we go. A galaxy 10 billion light years away shows us what it looked like 10 billion years ago. We're not seeing a snapshot of the current universe. We're watching a time-lapse in reverse. Every red-shifted glow is a whisper from history, and the farther the light has travelled, the more it stretches. This means that really distant galaxies don't just look faint, they look red. Sometimes the shift is so extreme that the visible light becomes infrared, or even radio waves. It's still the same light, it's just been pulled like taffy across an ever-growing universe. This is why redshift is such a powerful tool for astronomers. By analysing the spectrum of a distant galaxy, breaking down its light into individual wavelengths, we can measure how much it has been redshifted, and from that we can estimate its distance and the age of the light we're seeing. But redshift tells us more than just distance. It tells us about motion, history, and even the shape of the universe. When Hubble first discovered the redshift-distance relationship, it revolutionized cosmology. It showed that the universe was not static, as many believed, but expanding. Every galaxy, with a few local exceptions, appeared to be moving away from us, and the farther away it was, the faster it receded. That simple observation led to the conclusion that the universe had a beginning, a time when all matter and energy were much closer together, a time we now call the Big Bang. Today we use redshift to peer deeper than ever before. The James Webb Space Telescope, for example, is tuned to infrared light, making it especially good at spotting high redshift galaxies, those whose light has been stretched the most. These are the earliest galaxies, formed just a few 100 million years after the Big Bang. Their light has travelled for over 13 billion years, stretched across time and space, bearing the imprint of a young cosmos just learning to shine. But redshift also points to something more melancholy. As space continues to expand, and as that expansion accelerates, light from more and more galaxies gets redshifted beyond detection. Their signals dim, their details vanish. Eventually, the universe becomes quieter, darker, lonelier. In the far future, even the red-shifted light from our nearest galactic neighbours may fade beyond reach. Cosmic history, written in light, will slowly be erased, not by destruction, but by distance and silence. Yet even now, light continues to arrive. Ancient photons, born in stars long dead, glide across the cosmos and land gently in our instruments. Each one carries information, the chemical makeup of a galaxy, its motion, its temperature, its past. Some light travelled before Earth was born, some began its journey when dinosaurs still roamed the planet, and some is only just now leaving its source, destined to reach some distant observer billions of years from now, if they're still there to see it. It's humbling and beautiful to think of light as both a map and a memory. A map of where things are, and a memory of when they were. Each photon is a traveller, moving not just through space, but through time, and when we catch it, when we look up, we're not just seeing stars, we're reading a story written in colour and stretched by age. Redshift reminds us that everything we see is already gone, but in a way it's also still with us, carried forward by light, frozen in the moment it was born. In the end, redshift is more than a measurement, it's a language, the language of a universe in motion, a universe that stretches, grows and evolves. And though the past may be fading, its echoes remain, in every beam of starlight, in every spectrum, in every red glow from a galaxy far away and long ago. When we talk about the beginning of the universe, we tend to picture something vast and explosive. Stars flaring into life, galaxies forming in the blink of an eye, a cosmic fireworks show flung across space. But the truth is stranger. The universe didn't begin vast. It began small, very small, so small in fact that at its earliest moment it may have been tinier than a single atom. And not just small, but incredibly hot. We're talking temperatures of trillions upon trillions of degrees, a seething quantum froth so energetic that the laws of physics as we know them begin to wobble and blur. This was not a quiet birth. It was a roaring storm of pure energy. This first instant, often described by the phrase the Big Bang, wasn't really a bang in the traditional sense. There was no explosion into space. Instead, space itself began expanding. It was space doing the stretching, carrying energy, matter and time along for the ride. Within the tiniest sliver of a second, less than a millionth of a trillionth of a trillionth of a second, the universe underwent an astonishing growth spurt known as cosmic inflation. Imagine blowing up a balloon, only instead of puffing slowly, it suddenly expands faster than the speed of light. This doesn't violate any cosmic rules because it's not matter moving through space. It's space itself doing the expanding. During inflation, quantum fluctuations, those tiny jittery blips that exist everywhere in the vacuum of space, were stretched and frozen. These fluctuations became the seeds for everything. Galaxies, stars, planets, and eventually people. All of it started as tiny quantum wrinkles in an inflating balloon of space. When inflation ended, the universe kept expanding, but more calmly. The intense energy released began to cool, allowing matter to form. Quarks condensed into protons and neutrons. A few minutes later, these protons and neutrons fused into simple nuclei, mostly hydrogen, some helium, and a sprinkle of lithium. But things were still hot and dense, like the inside of a star. The universe at this stage was not a clear starry sky. It was more like the inside of a glowing oven. Particles of light, photons, were constantly colliding with electrons and bouncing around in every direction. It was a cosmic fog, bright but blind. Then, about 380,000 years after the beginning, something remarkable happened. The universe had cooled enough for electrons to settle into orbits around nuclei, forming the first atoms. Light was finally free to travel. This moment left a faint glow, the cosmic microwave background, that we can still detect today. It's the oldest light in the universe, a snapshot of the baby cosmos just starting to clear its throat. But we're still not talking about galaxies or stars yet. Those would take hundreds of millions of years more to form. What we had now was structure, the scaffolding of the universe. Tiny differences in density, those frozen wrinkles from inflation, meant some areas had slightly more matter than others. Over time, gravity went to work. It tugged on those denser spots, pulling in more material, slowly building the vast cosmic web we see today. So how small was the early universe? Well, if you rewind far enough, back to the very first moments, it may have been smaller than a proton, and yet it contained the blueprint for everything, every star, every galaxy, every thought you've ever had, all of it somehow encoded in that impossibly tiny hot beginning. It's almost poetic that the biggest thing we know, the universe itself, started out smaller than the things that make up atoms, and as it expanded and cooled, complexity emerged, from quarks to stars, from stars to planets, from planets to life, and all of it unfolding over billions of years, beginning with a moment of sheer, blazing simplicity. In truth, we don't know everything about the Big Bang. There are questions we're still chasing. What caused inflation? What happened before that moment, if before even makes sense? Was this universe the first and only one, or just the latest bubble in an endless froth of creation? What we do know is that the universe didn't need to start big to become majestic. It only needed the right rules, a little time, and a whole lot of room to grow. Today, when we look at the night sky, we're seeing the end result of that tiny hot beginning. Galaxies wheeling in slow spirals, nebulae glowing softly, planets quietly circling suns. All of it born from a speck that once could have fit inside your palm, had you somehow been able to hold the entire universe in your hand. It's hard to truly grasp. Our minds aren't built for that kind of scale shift, from subatomic to cosmic. But the universe doesn't ask for comprehension, just curiosity, and wonder, and maybe, just maybe, a little admiration for how something so enormous came from something so impossibly small. What does it mean for something to be big? We use the word all the time. Big houses, big oceans, big ideas. But the universe challenges even the most generous use of that word. It's not just large. It's not just vast. It might be infinite. Or it might just be very, very big. But how big exactly? And can something be large without having an edge? This is where things start to get weird. Let's begin with the edge question. Many people picture the universe as a kind of sphere, maybe like a giant snow globe with galaxies floating inside. That's a nice image, but it isn't quite right. According to our best measurements, the universe doesn't appear to have an edge. You can travel in any direction as far as you like, and you won't find a wall or a border or a sign that says end of universe, turn around. But that doesn't necessarily mean the universe is infinite. It could be finite just without a boundary, like the surface of Earth. You can walk in one direction forever without falling off the edge, but you're still travelling across a finite surface. It's just curved in a way that loops back on itself. That idea, finite but unbounded, is a real possibility for the universe. Cosmologists talk about this in terms of geometry. There are three main shapes the universe could take: flat, open, or closed. These don't describe physical edges so much as the way space curves. A flat universe is one where parallel lines stay parallel. Think of an endless sheet of paper. This kind of universe could be infinite, stretching on forever in all directions. According to data from the cosmic microwave background, particularly measurements from the Planck satellite, the universe appears to be very close to flat. Not perfectly flat, but within a margin of error so small that we haven't yet detected a meaningful curve. An open universe curves outward, like a saddle. In this geometry, space expands forever, and the universe is infinite in extent. It never wraps back on itself. If you travel in a straight line, you'll never return to where you started. You'll just keep going. A closed universe, on the other hand, curves inward, like the surface of a sphere. In this case, space is finite. Travel in a straight line long enough, and you'll eventually end up back at your starting point. Though it might take longer than the current age of the universe, there's no edge, just a cosmic loop. Now here's where things get a bit more philosophical. Even if the universe is finite, it's still astonishingly large. And if it's infinite, well, then it's infinite. That means infinite galaxies, infinite stars, infinite planets, and maybe, even this is debated, infinite versions of you. Somewhere out there, in the endless sea of cosmic possibilities, there could be another you listening to this same video, wondering the same things, but wearing a slightly different pair of socks. The problem with infinity is that it breaks intuition. Mathematically, you can define it, you can manipulate it, but experientially, it's slippery. You can't really feel infinity. You can only circle around it, trying to make sense of what it would mean. Even if the universe is infinite now, it may not have started that way. During the Big Bang, space itself was compressed into an incredibly hot, dense state. It could have been an infinitely dense point, or it could have been a very small, finite region. Either way, what matters is that it began expanding, and it hasn't stopped. In fact, the expansion of the universe adds another wrinkle. Space is still growing, and it's doing so at an accelerating pace. This expansion doesn't create an edge. It simply means that more space is appearing between things. Galaxies aren't flying apart like debris from an explosion. Instead, the very fabric of space is stretching, carrying galaxies along like raisins in a rising loaf of bread. And as the universe expands, more of it slips beyond our ability to see. Not because it's disappearing, but because light from those regions will never reach us. This creates an observable universe, a bubble around us, about 93 billion light-years across, within which we can see and measure. But beyond that bubble, the unobservable universe could be far, far larger. Maybe infinite, maybe not. Some theories, especially those emerging from inflationary cosmology and string theory, suggest that our universe might be just one pocket in a much larger multiverse, each with its own rules, its own space, its own time. In that case, the word big might not even be enough. Our universe could be just one bubble in a cosmic sea of other bubbles, each endlessly inflating, colliding, or branching off. But even if we stay within our own universe, the question of size becomes less about physical measurement and more about comprehension. Whether the universe is infinite or simply too large to ever traverse, the effect on us is the same. We are small, wonderfully, beautifully small, not insignificant, but nestled within something far beyond everyday human scale. There's a certain poetry to not knowing, to asking a question like, how big is the universe? And realizing that the answer might be forever just out of reach. That doesn't make the universe less interesting, it makes it more so. Because as long as the question remains open, so does our sense of curiosity. So, does the universe go on forever? We don't know. Maybe it loops, maybe it ends, maybe it expands eternally into regions we'll never visit or even glimpse. But here's something we do know. Even without an edge, the universe gives us boundaries to push, ideas to explore, questions to ask. And in the grand scheme of cosmic mystery, maybe that's the best kind of bigness there is. Billions, trillions, quadrillions. We say these numbers with ease, and we even understand them mathematically. But somewhere along the way, around the time we pass a few thousand, something strange happens. The numbers stop feeling real. They become more like incantations than actual quantities. We might say them, even understand what they mean in an abstract way, but we don't really feel them. And there's a good reason for that. Our brains weren't built to count galaxies. They were built to climb trees, chase prey, gather fruit, and navigate winding trails through the underbrush. Evolution handed us a mind honed for the immediate and the tangible. You know what 10 apples looks like, maybe even 50 or 100. But 10 billion stars? That's something else entirely. This is the psychology of scale. Our minds are most comfortable dealing with what we can see, touch, and use. A stone we can hold, a river we can cross, a day we can live through. Once numbers leap into the thousands or millions, they begin to slip out of reach. Billions and trillions just become background noise. Try it. Think of 1,000. Got it. Now imagine 1 million. Feels fuzzier, doesn't it? Now leap to 1 billion. Somewhere in that jump, your mental picture likely turned into a vague cloud of a lot. And it's not just distance. Time, too, becomes slippery. We're pretty good at remembering a few decades of history, maybe even a few centuries with effort. But when we talk about stars that formed 4 billion years ago, or light that has been travelling for 13 billion years, the human brain quietly bows out and lets the words wash over without truly registering their magnitude. But that's okay. In fact, it's expected. We weren't built for these numbers, so we cheat. We build tools to help us see. Metaphors, models, and mental maps become our cognitive stepping stones. We shrink the solar system down to the size of a basketball court. We compare Earth to a marble and the sun to a beach ball. We imagine grains of sand to represent stars, or stack sheets of paper to represent distances across time. One famous analogy tries to compress all of time, from the Big Bang to now, into a single calendar year. In that view, the entire human history we know would fit into the final few seconds of December 31st. Everything we've ever built, written, recorded, or dreamed, all packed into the last tick of the cosmic clock. We also use images, charts, diagrams, time-lapse videos, animations that zoom out from Earth to the edge of the observable universe. These aren't just pretty, they're vital. They translate magnitude into motion and numbers into feeling. We've even developed logarithmic thinking. That's the ability to scale numbers down exponentially, compressing vast differences into something we can sketch on a single page. It's how we compare the size of a proton to the width of a galaxy without needing a football field-sized blackboard. Logarithmic scales are everywhere in science, from measuring earthquakes to ranking the brightness of stars. They don't make the numbers smaller, but they make them graspable. Still, even with all these tools, there's something humbling about trying to wrap our minds around the scale of the cosmos. Consider the Voyager spacecraft. It's been travelling for over 40 years. It's billions of kilometres from Earth, and yet it hasn't even left the outermost boundary of our solar system. That's just our local space. Beyond that are the stars, the galaxy, the clusters, and the unfathomable web of everything. Our brains stumble under the weight of it all, and yet we keep trying. We teach children what a light year is. We build planetariums. We launch telescopes into orbit, not just to see, but to understand. Somewhere deep in our species is a compulsion to expand our mental map, to keep pushing against the limits of what we can comprehend. This isn't just about astronomy either. It's about empathy, economics, ecology. Whether we're dealing with the wealth gap, the number of species on Earth, or the scale of climate change, we're constantly running into problems of magnitude, numbers that are technically understandable but emotionally invisible. Knowing that 8 million tons of plastic enter the ocean each year is one thing. Feeling what that really means, that's something else entirely. And so we build stories. We create comparisons. We describe what 8 million tons would look like in garbage trucks, or how long it would take to clean it up with human hands. We try to connect scale to something personal, because that's the key, really, connection. When scale becomes personal, it becomes visible. And when it's visible, we can act on it, reflect on it, even feel awe for it. So no, we may never fully grasp what 10 trillion kilometers looks like, or what 100 billion galaxies really means. But we can stand beside those numbers, lean against them, and let them bend our imagination just a little more than before. In doing so, we stretch the limits of our cognitive comfort zone, not to conquer the scale of the cosmos, but to live peacefully with its immensity. The numbers may remain enormous, but we don't have to shrink in the face of them. We just have to learn how to listen. Imagine standing on a quiet beach. The tide is low, the sky stretches wide, and between your feet and the horizon are billions of grains of sand. Now picture this. For every grain of sand on Earth, on every beach, desert and dune, there are more stars in the universe. Not just more, but orders of magnitude more. The stars are not just uncountable, they outnumber the metaphors we have for describing them. And so we borrow. We steal metaphors from the world we know. Money, time, travel, buildings, insects, fruit. Anything to help shrink the cosmos down to something our minds can walk through without getting lost. Because while our numbers are accurate, our brains need more than numbers. They need stories. Think of Earth not as a planet, but as a speck of dust floating inside a vast Gothic cathedral. The cathedral is the galaxy, immense and dimly lit, its vaulted ceiling veiled by interstellar clouds. The speck drifts somewhere in a quiet corner, orbiting a candle flame, the sun, while far above and around other candles flicker. Some are barely visible, others flare bright for a moment, then vanish. The scale is impossible, but the metaphor lets us feel something we can't quite define, a kind of sacred smallness, or consider time as a map. If the entire age of the universe were compressed into a single calendar year, with the Big Bang at midnight on January 1st, modern humans wouldn't appear until late on December 31st. About 30 minutes before midnight. Every written word, every city, every song and story would fit into the final seconds. Everything we know exists in a whisper of cosmic time. Then there's the money metaphor. If $1 million were 1 second, $1 billion would be over 11 days. $1 trillion would be nearly 32 years. Now imagine 2 trillion galaxies. The math becomes meaningless, but the metaphor hints at the difference. Even travel is useful. Light moves fast, about 300,000 kilometers per second. If you could hop on a beam of light, you'd reach the moon in just over a second, the sun in about 8 minutes, and the nearest star in more than 4 years. To reach the centre of our galaxy, try 27,000 years, and that's just one galaxy out of those 2 trillion. We need metaphors because without them, the numbers float like driftwood, present but unanchored. With them, the vast becomes visceral. A child can understand that a single grain of rice means something different than a mountain of them. A person who's never seen a galaxy can still feel the weight of one when it's compared to a swirling city of stars. And it's not just for feeling small, it's also for feeling connected. Stories help us see our place in something enormous. The Pale Blue Dot speech by Carl Sagan is more than science. It's poetry. Earth is a mote of dust caught in a sunbeam, home to every king, poet, sinner, and saint. That metaphor didn't reduce us. It expanded us, even as it reminded us how tiny we are. Science thrives on precision, but humans don't. We thrive on pattern, rhythm, and analogy. That's why equations are only part of the picture. The rest is filled in by comparison, colour, emotion, and shape. When we say the universe is 93 billion light-years wide, that's a technical statement. But when we say that if the Milky Way were the size of a coin, the observable universe would still be larger than Earth, that's something you can feel in your chest. And the metaphors don't stop at physical size. Black holes become whirlpools, time becomes a river, space becomes a fabric. Each of these is incomplete, and often wrong in detail, but they get us close. They build a mental scaffold we can climb. They let us stare into the dark without blinking. Even the word universe is a kind of metaphor. It suggests unity, a single turning thing. Yet it contains multitudes, galaxies drifting like islands, stars pulsing with nuclear fire, clouds of dust forming the next generation of suns. The metaphor holds even as the facts multiply. In classrooms, museums, books, and videos, metaphors become lanterns. They light up parts of the cosmos we might otherwise pass by. Not because they explain everything perfectly, but because they give us something to hold on to, a way to stay grounded while floating in thought. Some of the most powerful science communicators, like Neil deGrasse Tyson, Brian Cox, or Sagan himself, use metaphor with the care of a sculptor. They chisel meaning out of the void. They make us feel the scale of the universe without collapsing under its weight. But metaphors are more than decoration. They're necessary tools. Without them, space is silent and empty. With them, space becomes a story, a place with shape, character, and scale. So how do you understand something too vast to imagine? You compare it to something else, something smaller, something human, a breath, a step, a speck, a year. And slowly, piece by piece, you begin to build a bridge between your finite mind and an infinite universe. You may never walk all the way across it, but even standing on the first plank is enough to feel wonder. Picture this, a universe inside a computer, not a galaxy, not a star system, not even just a solar neighbourhood, but a full universe stitched together by equations and code. It may not burn or breathe, but it evolves, collides, expands, and grows, just like the one we live in. This is the realm of cosmic simulations, and it's one of the most powerful tools astronomers have for answering impossible questions. The real universe is not something we can experiment on directly. You can't fast-forward a galaxy to see how it will evolve. You can't rewind time and tweak the laws of physics to test a new theory. But inside a computer, you can. That's where simulations come in. Massive digital test tubes filled with virtual matter, governed by real physics and powered by some of the fastest supercomputers on the planet. At the heart of these simulations are the laws of gravity, thermodynamics, dark matter behavior, and fluid dynamics. You start with a box, an imaginary cube of space, maybe 100 million light-years across, and fill it with tiny particles that represent clumps of matter. You let the laws of physics act on them. Over time, matter pulls itself together, structures form, galaxies spin up, filaments emerge, voids open wide like cosmic lungs. It becomes a model of reality grown from the ground up. One of the most famous of these efforts is the Illustrious simulation. Released in 2014, it modelled a portion of the universe with 12 billion resolution elements. That means 12 billion chunks of space, each calculated with painstaking precision, tracking dark matter, gas dynamics, star formation, black hole feedback, and more. Illustrious produced galaxies that looked eerily real. Not perfect, but close enough to start asking serious questions about why galaxies form the way they do. Then came Illustrious TNG, the next generation, which expanded the scale, improved the algorithms, and created even more lifelike structures. It showed how cosmic feedback from black holes could shut down star formation, how galaxies change shape over billions of years, how the cosmic web grows and stretches across unimaginable distances. Another landmark project is the Millennium simulation. Completed in the early 2000s, it followed over 10 billion particles of dark matter evolving across a region more than 2 billion light-years wide. That's a digital box containing a meaningful slice of the observable universe. Millennium helped researchers understand how large-scale structures form, not just galaxies, but entire clusters, walls, and superclusters. But it's not just about numbers. These simulations are beautiful. They produce images and videos that look like cosmic lava lamps, threads of light connecting brilliant nodes of matter, spinning and folding and breathing like something alive. You're not just looking at data. You're watching a story unfold across billions of years, rendered in three-dimensional time. And here's the magic. When simulations match the universe we observe, it tells us our physics is probably on the right track. When they don't, it tells us we've missed something important. Either way, they help refine our understanding. They've also taught us just how important dark matter is. Without it, simulated galaxies fall apart. They don't clump the way real ones do. They don't form elegant spirals or dense cores. Simulations helped confirm that something invisible, something 5 times more abundant than regular matter, is sculpting the cosmos behind the scenes. And it's not just dark matter. Simulations have shown how galaxies collide, how black holes influence star formation, and how the early universe's violent expansion led to the delicate web we see today. They've become laboratories for testing ideas we could never explore in real time. But perhaps the most remarkable thing about these simulations isn't just that they're accurate, it's that they're intuitive. They take dry equations and bring them to life. They let us see the poetry of physics at work. Gravity becomes a sculptor, shaping filaments and halos. Gas becomes paint, swirling into galaxies. Energy becomes motion. Time becomes a sculpting chisel, carving complexity into simplicity, then back again. Some simulations are interactive. You can fly through them, pause them, zoom in and out. You can click on galaxies and see their histories, their mergers, their starbursts. You can trace the lineage of a single cluster across billions of years. It's like being able to rewind the universe and press play from any angle you like. But these projects are not built overnight. A single run can take months and require the combined power of thousands of processing cores. It's like launching a rocket made of math. You hit go and wait while the numbers evolve, hoping that what comes out will resemble the sky we see overhead. Sometimes they don't. Sometimes simulations produce too many dwarf galaxies, or galaxies that are too massive, or stars that form too quickly. These discrepancies aren't failures, they're clues. They point to gaps in our knowledge. They whisper about missing pieces in the cosmic puzzle. And because simulations can be rerun, tweaked and tested again, they become engines of discovery, a way to narrow down the possibilities, a way to see not just what the universe is, but what it might have been had things gone just a little differently. They also allow us to visualize the unseeable. We can't observe the full three-dimensional structure of the cosmic web directly. We only get snapshots from our vantage point inside one galaxy. But simulations can show us the full pattern, the hidden architecture of matter, the skeleton of the universe. And as the technology improves, we're approaching a point where these virtual universes are nearly indistinguishable from real telescope data. Some are so accurate that astronomers can test new instruments on simulated skies before ever pointing them at the real one. There's a deep irony here. We often think of computers as cold and lifeless, but through them we've created some of the most vivid and moving portraits of the cosmos ever made. Portraits that pulse with realism, but also with imagination. Because in the end, a simulation is more than just code. It's a translation. It takes the abstract language of the universe and turns it into something we can watch, explore, and even feel. And in doing so, it brings us closer to understanding not just the cosmos, but our place inside it. There was a time when we believed the entire universe revolved around us, literally. The stars danced across the night sky because we were standing still, planted at the centre of all things. The sun, the moon, the wandering planets, they circled Earth like celestial courtiers, and we, the crown jewel of creation, looked on. That idea, known as geocentrism, wasn't born from arrogance so much as observation. It certainly looked like everything moved around us, and for millennia the illusion held. It was comfortable, reassuring, a cosmic stage built just for us. But science is a relentless editor, and eventually someone tugged at the curtain. Enter Copernicus. In the 16th century he dared to suggest that perhaps the sun was at the centre, not Earth. A radical shift, one that bumped us out of the spotlight. Then came Galileo pointing his telescope to the sky and seeing Jupiter's moons orbiting something other than us. Then Kepler and Newton, and suddenly the whole machinery of the heavens was turning on new gears. The shift was more than just scientific, it was philosophical. It told us something uncomfortable. We're not the centre, not of the solar system, not of the galaxy, not even of the observable universe. This perspective became known as the Copernican principle. At its heart is a simple idea. We are not special. There's nothing particularly privileged about our location in space. No throne at the centre of creation, no spotlight of divine geography, just a planet orbiting a star in a quiet corner of a typical galaxy among trillions of others. It sounds harsh at first, like being handed a note that reads, "You are here, and it doesn't matter." But there's another way to read that note. Modern cosmology embraces this humility. It's not a punishment, it's liberation. The laws of physics apply equally everywhere. The same particles, the same forces, the same beautiful mathematics govern galaxies a billion light years away as they do your cup of tea. We don't live in a universe made for us, but we live in one that we can understand, and that's astonishing, because even though we're not at the centre, we can still map the stars. We can measure the cosmic microwave background, the faint echo of the Big Bang. We can build telescopes that peer back over 13 billion years. We can simulate entire universes in computers. In a way, we're not at the centre of space, but we're at the centre of perception. We see the universe, and in doing so, we shape its meaning. There's a paradox here. The more we learn how insignificant we are in space and time, the more extraordinary it becomes that we can comprehend it at all. Our brains evolved to throw spears and pick berries, not to understand quantum fields and general relativity. And yet, here we are, counting photons from distant galaxies, debating the curvature of space, wondering whether the universe is infinite or just really big. That ability might be what makes us special, not our location, but our curiosity. And there's beauty in letting go of the idea that we're the centre of everything. It means the universe isn't about us, but we're part of it anyway. A tiny thread in a vast tapestry, a brief flicker in cosmic time, yet somehow still able to wonder. Think of it this way. You're not the centre of the forest, but that doesn't make the forest any less beautiful. You're not the centre of the ocean, but you can still float, still swim, still feel the waves. The universe isn't built for us, but it allows us to exist, to observe, to ask questions, and in doing so, We become part of its story. Even in ancient times, people looked up and saw patterns in the stars, constellations, myths, guides for crops and seasons. They weren't trying to claim the universe. They were trying to understand their place within it. That's what we still do today, with far better tools and much larger questions. Are we the center of anything? Not in the old sense, not in the spinning sphere, deity-favored, everything orbits a sense. But perhaps we are the center of our own experience, the lens through which the universe sees itself, a tiny patch of consciousness, blooming on a rock drifting through space. And maybe that's enough, because in all this vastness we've discovered something remarkable. Meaning doesn't have to come from being central. It can come from connection, from curiosity, from the fragile, fleeting and deeply human act of looking up and asking, well, what else is out there? So while the universe may not revolve around us, our thoughts still reach into its furthest corners, and perhaps that's what makes this journey worthwhile. How big is the universe? It's such a simple question, so neatly worded, so temptingly clear, and yet the more we try to answer it, the more it slips through our fingers. It's like trying to catch a wave with a teacup. Maybe the question itself is flawed, not because it's unimportant, but because it comes from a place that our minds were never designed to go. Big means something very specific when we're talking about roads, mountains, cities, or even planets. But once you venture into galactic territory and beyond that into clusters, superclusters, filaments, and finally into the unknown dark beyond the observable edge, big loses all grip on reality. How big is something with no clear boundary, no edge, no measurable end? The universe may be infinite, or it may be finite but unbounded, like the surface of a sphere, but in more dimensions than we can picture. It may be only one of many in a multiverse, and even if we could one day pin down a number, some final cosmic diameter, it would still be changing. Space expands, light travels, horizons shift. There is no static measurement in an unfolding cosmos. Perhaps the better question is not how big, but how does it feel to live inside something that enormous? It feels humbling, it feels a little dizzying, but it also feels strangely peaceful. Because once you accept that the scale of the universe is fundamentally beyond us, that no metaphor, no simulation, no spreadsheet can truly contain it, you begin to see something else. You begin to see that awe and wonder are not signs of failure. They're the only proper responses. Trying to measure the cosmos is noble. Trying to understand it is thrilling. But being overwhelmed by it, that's a kind of wisdom too. We often think of knowledge as control, but in this case, knowledge leads us directly to mystery. The deeper we look, the more intricate the patterns, the more vast the distances, the older the light. The more we learn, the more we realize just how much we don't know. And in that gap, in that soft, silent space between questions and answers, there's a kind of beauty that doesn't need solving. There's something poetic in knowing we'll never fully grasp the totality of where we are, that we'll never see all the galaxies, that there will always be more stars hidden behind time and distance than visible to our eyes. And yet, here we are, a small species on a rocky world staring out into everything, building tools to stretch our sight, crafting stories, simulations, equations, and songs about what we see. Even if the universe is too big to know, we keep reaching, we keep wondering, we keep asking, and that in itself is cosmic. There's a paradox at the heart of all this. The more we zoom out, the more we feel the quiet pull inward. When you stare into the vastness, you start thinking about the smallness of your life, your memories, your breath. The universe doesn't speak in words, but it reminds you that everything changes, that even stars fade, that time flows in every direction, whether you notice or not. And strangely, that thought can be calming, because if the universe is too big to measure, then maybe it's also too big to worry. All the little stresses, the anxieties, the tangled to-do lists, they shrink under starlight. Not because they're unimportant, but because they're temporary, just like everything. There's peace in letting go of needing to get it, You don't have to understand the full scale of the cosmos to feel its presence. You don't have to measure the distance between galaxies to enjoy the warmth of the night sky. You don't need to memorize redshift formulas or parsec conversions to be moved by the idea that light from a star can travel for billions of years just to land on your eyelid. Sometimes the only reasonable response is to breathe in and feel small and safe and still. So maybe the question isn't, how big is the universe, but how open are we to wonder? It's a softer question. It doesn't demand an answer. It invites a moment. And if that moment leads you into sleep, into dreams filled with spiral galaxies and glowing filaments and star fields too vast to count, then maybe the universe is doing its job. It's not there to be solved like a puzzle. It's there to cradle you, to whisper in photons, to remind you, quietly, endlessly, that there is more than we can know, and that knowing that is enough. So go ahead, close your eyes, let your thoughts drift past the moon, past the planets, past the humming silence between stars. Imagine the great cosmic web stretching beyond sight. Picture entire galaxies blinking gently in the dark. You're not meant to hold it all in your mind, just to feel it brushing against the edges of your thoughts, like waves against a shore you can't quite see. And maybe that's all the answer we need. Can we comprehend the size of the universe? Maybe not. At least not in the way we usually try to. Not with numbers or measurements alone. Not by stacking trillions on trillions like building blocks and hoping it forms something we can hold in our heads. The universe is too vast, too layered, too strange for that. But that doesn't mean we can't understand it in some way. Maybe understanding doesn't have to be numerical. Maybe it can be emotional. Maybe it can be felt rather than solved. Because when you step outside on a clear night and look up at the stars, you don't need a calculator to feel small, or quiet, or amazed. You just feel it, deep in your chest, as though something enormous has brushed past the edge of your awareness. A presence you can't quite name, but one that leaves you still. We asked at the beginning whether the human mind can grasp the scale of the cosmos, and it turns out the answer might be both no and yes. No, because our brains were not built for this, not for light years or superclusters or expanding space. We evolved to chase gazelles and find shelter before sundown. The universe didn't need to make itself comprehensible, it just needed to be. And yet, yes, because we found ways to reach beyond those limits. We built telescopes and simulations, metaphors and models. We sent probes into the void and caught whispers of the Big Bang. We mapped the background hum of creation. We taught ourselves to wonder. And wonder is a kind of understanding. Not the kind you can file into spreadsheets, but the kind that settles in your bones. That kind that sits with you, quietly, like starlight pooling in a still pond. Maybe comprehension doesn't always look like clarity. Maybe it looks like stillness, like acceptance, like awe. You don't have to solve the universe to feel part of it. You already are. You're a brief arrangement of atoms in a long cosmic story. You're stardust with dreams. You're the universe noticing itself for just a moment. A quiet ripple in an ocean of space and time. So don't worry if it's too much to picture. Don't worry if the light years and parsecs blur together. Let them. Let the numbers dissolve into starlight. Let the galaxies drift past slow and silent, like jellyfish in a dark sea. Let the mystery hold you, because this isn't a puzzle to solve, it's a place to float. Close your eyes and imagine drifting, weightless, unhurried, through a sea of stars. There's no destination, no need to arrive, just light and distance and the gentle unfolding of time. And in this stillness, maybe that's where the truest kind of understanding lives. Thank you for joining this journey, for following the thread from Earth to the edge of what we can see, and beyond that, into the places we can only imagine. Thank you for your curiosity, your patience, your willingness to sit with questions that don't have easy answers. You're not alone in this wonder. All across the world, people are looking up, listening, wondering, asking, how big is it all? Where does it go? What does it mean? And maybe tonight, as you fall asleep, you'll carry a little piece of that with you. A sense of scale that isn't about size but feeling. A sense of peace that comes not from knowing everything, but from knowing you're part of something vast and beautiful and still unfolding. Rest well, dream of galaxies, let the stars keep watch,